Alright, so my name is Eric Cochran. I'm a computer science and applied math major here at Texas A&M University. Whoop. And today we're going to talk about stack overflow attacks. So in this case, we're going to exploit a vulnerability in string copy. The reason this vulnerability exists is because string copy doesn't check the size of the incoming string with the size of the buffer. So essentially that's what we're going to be exploiting, the fact that it can overflow a buffer and rewrite, basically rewrites locations in memory that it shouldn't have access to. And using that, we can kind of mess up the stack in a way that we can inject code into the buffer and overwrite the return address that's stored in the stack to essentially get it to point back into the buffer where we've kind of maliciously embedded this code and get it to execute that. At the end of this, we should have access as the root, which, as we know, if you have access to the root, you can run any command on a system and you could do a lot of damage. So that's bad. Right, so here's the fun part. We're going to look at two different pieces of code. Stack.c is going to be the one with the vulnerability. Again, we talked about the fact that string copy does not do any kind of bounds checking. So this is what's going to introduce the buffer overflow problem into this piece of code. So outside of this function, we have another buffer that will not cause a buffer overflow. File called bad file, which is going to contain our malicious code. So that's where we're going to put the shell code to get to the root. And then just some other basic stuff. Read the file into the string buffer. Call the function with the exploit, and then we just have this little print function at the end to show that, well, we return property, but you'll see that when we successfully implement the exploit, you won't see that print statement because we'll have changed the return address. Right. Is that true? Wait, is that true? No. Does it say that? Okay, so now we're at the fun part, where we're actually going to write our exploit. I already have the exploit written, so I'll go over some of the key components of it. Again, we have the shellcode that we've already talked about. This function is going to return the stack pointer, and that's one of the things we're going to try to use to guess the return address that we need to feed to the processor. So that return address will hopefully point back to our buffer and into the NOP sled, which will then run into the shellcode and hopefully get us to access the command line with root privileges. So we have our buffer bad file, which is what the stack is going to read from and where we're going to get our overflow. So here I just have the size of the shellcode. The length of the buffer, but I mean we already know, we set that, so we know it's 517. Here, this offset is going to be passed down here to the return address. So I'm going to try to adjust it so that we get farther into the NOP sled and closer to executing the shellcode, but we'll talk about that later. This is from LF1's paper. I'm not entirely sure why we would need this. I think if we wanted to do an exploit and run another command through the command prompt, it would adjust the offset to account for that. We're really not going to use this. Um, and I should just take it out, but whatever. Then here we need to typecast the pointer address, because the pointer address, and I think we initialize it as a char. Right, well, anyway, we need to typecast it to a long pointer. And then here, this is what's providing the NOP sled, which gives us a bound for error. So we don't, part of the problem with this exploit is that we don't exactly know where our malicious code is going to be. So using a NOP sled, you kind of improve the chances that you're going to land in the section that will eventually just kind of go through all the NOPs, slide through all the NOPs, and then get to our malicious shellcode. I mean, if we wanted to do something really crazy, like maybe we could allocate a bunch of memory and then just just max out the memory and fill it with NOP sleds. I mean, we'd increase our probability of landing in the malicious code, but we're not going to do that. Most programs have a relatively shallow stack, so we can get away with this. Again, here, this is what is calculating the return address. Well, it's what's pointing the return instruction that we're overriding to our NOP sled. So that's that bit. Okay, so here, this is what this is the section where we're trying to override the return that's on the stack. So we're overriding 300 entries, and we're sending them to the return address that we want, which again is into our NOP sled. So this is a little illustration that I included, which helps me figure out what's going on. So this first section is this part. We just have a whole bunch of return addresses that when the machine executes them, it should land into this NOP sled, and then all these will just kind of boom, 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 execute and go to our shellcode and run this. And then there's some leftover NOPs, but I don't think they'll do much. I think you'll probably just segfault eventually. So then this is where we're overriding some of the NOPs in the buffer. So it's starting at memory location 420, and it's just going to write 25 bytes of our shellcode. So yeah, that's this piece. And then because we overwrote the terminal character for the array, we replace that. Then I have some things just printing out information for debugging. So that's pretty much the majority of the exploit. And then here it's just writing the bad file, which is what we're going to pass to the stack program. So now that we have those two programs, let's go ahead and see what it looks like in the command line. I want to retype this, so maybe I can find, well, I showed you how to compile the stack. You need to be root to enable executable stack and to turn off the stack guard, but we already have that. Right, so we already have the stack one. So we're just going to compile the exploit, and that one doesn't need any special protections since this isn't the file that we're exploiting. So we can run that as a regular user, and then we're going to execute the exploit. So that just generated our bad file, and now we're going to run the stack, and hopefully we should get root privileges. Alright, so we're now the root. We can prove that. So our effective user ID is the root. There's some things we can do to change our our actual user ID to the root, but we'd have to make another file and then basically execute that file, giving us the user ID as the root, Right.